Hello, ladies and gentlemen. Mr. Dorfler here with your next daily dose of Dorfler. Here we are after our conversation on redox reactions. As a little bit lengthy of one, but I kind of gave you a fair heads up on that. Today's video should hopefully not be as long. We're going to be doing a little math today. All right, so you will need a calculator. If you possibly want to have your periodic table on hand. We are going to do some things that we have done in the past, but you will need to utilize your periodic table when you are doing a few things here, okay? What we're going to be talking about is actually making solutions, okay? And we talk about making solutions, we're going to be making solutions according to appropriate concentrations, all right? And we're talking about aqueous reactions and solutions. And so we're talking about molarity, all right? We can have two or even more solutions of the same substance, okay? But we can have a drastically different concentration of those substances. And that's what we need to evaluate in today's discussion is how do we determine and create solutions of certain concentrations, all right? And so we utilize the concept of molarity, and this is important. This is your formula we're going to be working on for a good portion of today's discussion, is molarity, which is denoted as a capital italicized M, is equal to the moles of solute. Remember, solute is a substance that is in the, it's basically what is being dissolved, okay? The solvent is what is found to be in greatest amount. And so moles of solute, and then we take moles of solute divided by volume of solution in liters. Very important about liters, okay? So when we are mixing a solution, to create a solution of known molarity, you have to weigh out the mass, okay? And when you weigh out the mass, you have a pretty good idea how much mass you have. I mean, it makes sense. You measured it using a scale. You know how much it is. And depending on what the substance is, you can take the amount of that substance that you have weighed out and utilize that substance's molar mass to help determine how many moles are present. Okay? Once you do that, that solute that you just measured out is going to be added to what's called a volumetric flask, okay? I'm not certain if I showed these to you before early in the year, but it's basically just a flask with a really skinny neck, and it's got a single line on the neck, and that single line tells you exactly what the volume is of that solution that you just made, okay? So you know exactly what your concentration is going to be after you calculate that. So we're going to spend a few times utilizing the molarity equation to help solve for any of these variables here. You know, this is an equation. This is a formula. So just like any other formula we've ever used or you've ever used, we can rearrange this to solve for whatever is unknown. Okay, so let's look at this example here. Says calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate, given the formula Na2SO4, in enough water to form 125 mils of solution. So what do we know? Well, we know the mass of the sodium sulfate, and we know what our final volume has to be. Okay, but a few things here. Okay, when we're trying to determine the concentration, therefore the molarity of the solution, we have to have moles and we have to have a volume in liters. So let's first concentrate on determining how many moles of sodium sulfate we have. So as we see here, to determine the moles of sodium sulfate, we take the amount that we have, 23.4 grams, and utilize the molar mass of sodium sulfate. So it's 142 grams per mole. But 142 grams goes on bottom because we're solving for moles, okay? If you don't remember how to determine the molar mass of a substance, I suggest you go back a couple chapters. Remember, you have to take the formula and utilize the amount of each element in the formula alongside its respective mass from the periodic table to determine the molar mass. So we find that we have 0.165 moles of sodium sulfate present. Sorry. Next, we need to figure out what our volume of the solution has to be. We are told that our final solution needs to be 125 milliliters. But as I emphasize in the formula for molarity, the bottom number must be volume in liters. So we must take the milliliters and convert that to liters. So where we take, I'm just going to move that there, the 125 milliliters and then convert liters, 1 liter over 1,000 milliliters. Again, there are 1,000 milliliters in a liter. So we use that conversion factor. It eliminates our milliliters, leaves us with liters, and we have 0.125 liters. Now, we can finally calculate our concentration or our strength of our solution here. Take the 0.165 moles divided by the 0.125 liters, and we get our final answer. As you see here, they have 1.32 moles per liter. Well, when you give your final answer, it must have the unit of capital M. Okay, so 1.32 molarity, 1.32 capital M. And this is how we receive all of our solutions in our storage room here. It always tells us the concentration in molarity based off the volume that we are given. All right, oops. Let's do our own example here. It says calculate the molarity of a solution made by dissolving 5 grams of glucose in sufficient water to form exactly 100 milliliters of solution. All right, so hello, I'm going to go boop. And we're going to dim the lights ever so slightly. So again, molarity is, we don't need to be that zoomed in. Molarity is equal to moles over liter. Well, we are told that we have 5.00 grams of C6H12O6, but we need to determine how many moles of this we have. And again, if you don't recall how to do this, look it up. We've done it numerous times, but the molar mass of glucose is 180 grams and 1 mole on top. And so grams cancel out, and we are left with 0.027. Ooh, you can't see that. Sorry, 0.0278 moles. Okay, so I'm just going to put that on top, 0.0278 moles. And we have 100 milliliters that we need to convert to liters. Milliliters cancels out, and we're left with 0.1 liter. So we put that in our formula. And if you want to pause right now to calculate this, go ahead. But you should have a final answer of 0.278 capital M. And that is your answer for that problem. Okay, I'm going to continue on. If you need to go back to this, just hit the rewind and rewatch it at your leisure. Okay, we're going to do a couple more problems here. This sample exercise asks us to determine the molar concentration of each ion present in 0.025 molar aqueous solution of calcium nitrate. Now, we again have done something similar to this in a previous chapter, where we have to determine, looking at the ratios of elements in a particular compound, and determining how many would be present. We're doing the same thing here. Okay, so we have calcium nitrate. First thing is we need to figure out what the formula for calcium nitrate is. Okay, calcium ions and nitrate ions. The formula is going to be CaNO3 So nitrate's in parentheses. And so we know that there is 0.025 moles of calcium nitrate per liter. Okay, that's what this means, the molar, okay? Moles per liter. So if we were to have calcium nitrate break up into their ions in an aqueous solution, we have to look at the ratios, okay, of calcium and nitrate ions, okay? There, in each molecule of calcium nitrate, there's one calcium and two nitrates. So we're going to use the mole ratio like we've seen before, where we have 2 moles. Again, that 2 moles comes from the subscript of nitrate for every 1 mole of calcium nitrate. Okay, so then we use our mathing skills. We multiply 0.025 times 2, and we get a final answer, a final concentration of 0.050 molar. Okay, same thing for the practice exercise. What is the molar concentration of potassium ions in 0.015 molar solution of potassium carbonate? All right. First thing is we need to determine our formula for potassium carbonate. Okay. We've got potassium, it's K plus, carbonate, CO3, 2 minus. We have to whoop their charges, whoop, to where we get K2CO3. Potassium is our focus on this problem. So we are trying to figure out what the concentration is of potassium ions. So again, we always put down what we are given. We are told that we have 0.015. I'm going to go ahead and expand out our concentration. Okay. K2CO3. That way I can cross out the appropriate units. And again, looking at the ratio here, there are 2 potassium ions for every 1 carbonate ion. So it's a 2 to 1. So in every molecule, there's going to be 2 potassium ions that are going to dissociate. So we have 2 moles of K plus over 1 mole of K2CO3. So this allows for moles of K2CO3 to be eliminated. And then we're going to be left with moles per liter, which does translate into molarity. And so we take 0.015, multiply it by 2, and we get a concentration of 0.030 moles of K plus. Or not moles, but molar concentration of K plus. And don't say moles. That would be the improper unit. Okay? So again, it all comes back to the subscripts and the ratios in the problem. Okay? All right. Next, continuing on with our learning. Now we're going to take the molarity equation and rearrange it to solve for our other units. Okay? So here we are asked to determine how many grams of sodium sulfate are required to make 0.350 liters of 0.500 molarity of sodium sulfate. Okay, I'm just going to move this over here. So we got to take our molarity equation, moles over liters of solution, and we need to rearrange it to solve for moles. Can we do that by taking liters of solution and multiplying it on both sides, and we get this new formula right here. Okay? Once we have it set and rearranged for moles, we can go ahead and input our values. Again, we were told we have 0.35 liters of solution and a concentration of 0.5 molarity. So if we break down molarity's units of moles per liter, we can cancel out the liters, leaving us with moles, and we get the number of moles. That's not the end of it, though, because we were asked to figure out how many grams of sodium sulfate do we have or are required to make this particular concentration of a substance. So then we take the 0.175 moles of sodium sulfate and again utilize the molar mass of sodium sulfate, this time solving for grams, so grams goes on top, and we find that we need 24.9 grams of sodium sulfate to make that particular scenario work. Okay? Next, practice exercise. How many grams of sodium sulfate are there in 15 milliliters of 0.50 molar sodium sulfate? And then how many milliliters of 0.5 molar sodium sulfate solution are needed to provide 0.038 moles of this salt? So this is a two-part question. Okay, the first thing is, I'm going to minimize this and get back into this. First thing is, I need to look at this equation. That is a capital italicized M, if you can't tell, moles per liter. Okay? The first question, however, is asking us to determine, let me go back to it, how many grams of sodium sulfate are there in 15 milliliters with a concentration of 0.5 molar? Okay? So I need to solve for moles of sodium sulfate. So that's going to be molarity times liters. And so I have a concentration of 0.50 moles per liter. Again, that's what M is. It's moles per liter. Multiplied by, well, my volume in liters. But we were told that we have 15, sorry, not 0.15, we have 15 milliliters. I'm just going to double check that before I go any further. Yep. So we need to convert milliliters to liters, convert again, and we get 0.015 liters. So 0.015 liters. So we go ahead and solve for how many moles we have present, and we get 0.0075 moles of sodium sulfate. But we need to determine how many grams do we have. So again, we're going to use the molar mass of 142 grams of sodium sulfate per mole. And we're going to find out that we have 1.1 grams as our answer. So again, I just took the molarity formula, rearranged to solve for moles, calculated my moles, used molar mass of sodium sulfate to determine how many grams I had. The next part of the question says, how many milliliters of 0.50 molar sodium sulfate solution are needed to provide 0.038 moles of this salt? Okay, so again, going back, excuse me, going back to this formula, we are trying to figure out milliliters, but milliliters are hidden within the liters itself. So we're going to rearrange this equation. We're going to multiply both sides by liters and then divide both sides by molarity. So we're going to get liters is equal to moles over molarity. And so we're told what our concentration is, and that is how many moles we have. That is 0.038 moles of sodium sulfate. We know what our concentration is of 0.5 molar. We get 0.076 liters. But again, excuse me, we need to answer this in terms of milliliters. So we're going to take the 0.076 liters and multiply it by 1,000 milliliters per liter, and we're going to get final volume of 76 milliliters. So over the last few questions, we haven't changed anything in terms of what we're using. All we've simply done is done a little bit of algebra and rearranged the molarity equation to help us solve for each variable. And since we've been talking about concentrations, volume, and all that fun stuff, we're going to get into our last topics of the day. okay? And that is dilution, all right? Now, I'm sure you've heard of dilution before. Sorry, my voice is getting a little crackly here. I'm sure you've heard of dilution before. Basically where we take a concentrated solution and make it less concentrated, okay? In the scientific lab setting, this is a highly necessary skill to have. Mr. Serbic and I do this quite often, where, as I said, we are given these solutions from our manufacturer, and they are typically in higher concentration. And they ship them in higher concentrations because we can then go and manipulate that concentration of solution, make it to exactly how we need. And by doing so, they don't have to send us barrels of random concentrations, okay? We can get a higher concentrated solution and use the process of dilution to help us bring it down a notch and make that product last longer, and we can save some space in our storage area. Anyway, what you do is you get a certain concentrated solution. You take out a specified volume with a pipette, put it into a volumetric flask like you see here, okay? And you add that concentrated solution into the flask. You then use water or another solvent to get up to that line indicating a certain volume. And wouldn't you know it, that there is a mathematical process that you can use in order to help determine how much of the concentrated solution and how much of the solvent do you need in order to do so. So you get the formula of MC times VC is equal to MD times VD. Now, MC and VC, the subscripts of C stand for the concentrated solution's concentration and volume. The D is for diluted concentration and diluted volume. I also wrote down after the fact, actually fairly recently, after you've already been given these notes, of thinking of it this way. MI times VI equals MF times VF. The initial concentration and initial volume is equal to the final concentration and times the final volume, okay? And so basically what we're going to do is we're going to be given a volume of a certain solution with a specific concentration, and we are going to dilute it. So that equal signs almost means like that's the process of diluting, which is going to lead to our new concentration, our MF, and our new volume, our VF, okay? So those are handy ways to think about it. So let's take a look here. How many milliliters of 3.0 molar sulfuric acid, H2SO4, are needed to make 450 milliliters of 0.10 molar H2SO4? So before we even get started looking at how they solve this, we have to identify what information we are given, okay? So we know that when we are talking about the molarity or concentration, either it being the MI or MF or MC or MD, however you want to look at it, those are always going to have molarity, okay? Whenever we're talking about milliliters or liters, you're going to be talking about the volume part, the V of the equation, okay? Now you might ask yourself, well, why is it in milliliters? Well, because mathematically speaking, most certain units are going to cancel out, and you don't necessarily always have to convert between milliliters and liters, okay? So let's look at how they solve this here. I forgot to put my dimmer back up. Anyway, so we're going to take this equation, whatever one you want to use, whatever way works best for you. We're going to take this equation, and basically we see that we need to make 450 milliliters of 0.1 molar. So we are diluting a 3 molar concentrated solution to 0.10. So this is going to be our final concentration and our final volume. This is our initial concentration. So we have to figure out how much volume do we have to initially add in order to make this particular solution. So we take this equation and rearrange it to solve for VC. So you're going to have MD times VD divided by MC. Okay? So, excuse me. Now, I like what they do here. Okay? What they're doing here, okay? What they're doing here is simply showing you that there's actually two ways that you can solve questions about dilution. Okay? And you could do it this way, where you have to determine, how many moles of sulfuric acid you have, then determine, they're both using the molarity equation and just kind of going back and forth here. Or you can use the equation we just saw, okay, where we're going to take the volume of the concentrated solution, the initial solution, and we're going to solve for it. So we're going to take our 0.10 molar concentration, our final concentration, multiplied by 450 milliliters and divided by 3.0 molar. As you saw, that the units of molarity, the capital M, are going to cancel each other out, leaving us with a unit of milliliters, which is what we need to use in our final answer. So basically, once we do our math, we're going to find out that we need 15 milliliters. Well, what does that mean? Well, that means that we are going to take 15 milliliters of our stock concentrated solution of sulfuric acid, so the 15 milliliters of the 3.0 molar solution. We're going to put it into a volumetric flask, and we're going to fill it up to the line that says 450 milliliters. That's how we make a solution. So we're taking this amount out of the 3 molar solution bottle, placing that 15 milliliters into a 450 milliliter volumetric flask, and filling it up with water all the way up to that line, and we will have a concentration of 0.10 molar. Okay? So let's try our own here. We have a 3-part question. So the first one is, what volume of 2.50 molar lead 2 nitrate solution contains 0.05 moles of lead 2 ion? So it's kind of going to be incorporating everything we've talked about today. So let's do this one at a time. Okay. So we're doing A. Okay. Well, what we're going to be doing is really taking this equation and solving it for liters. So it's going to be liters is equal to moles over molarity. Okay. And so we're simply going to take our, take our substance. One second, I gotta go refill my water here, folks. All right, sorry about that. All right, so we have our 0.05 moles. We have our concentration of 2.50 molarity. And when moles of these two units cancel out, we're going to be left with 0.02 liters. So that is the first part of the question, okay? 0.02 liters. Next part, how many milliliters of 5.0 molar potassium chromate solution must be diluted to prepare, that's dichromate, must be diluted to prepare 250 milliliters of 0.1 molar solution. All right, so getting back to this now. Again, using the dilution formula now. MC times VC is equal to MD times VD. Okay, what do we know? Well, we know what our final concentrations and volume will be. We also know what our initial concentration will be. So we need to figure out what VC is. So VC is going to equal MD times VD over MC. So our diluted concentration is 0.10 molar. Our final volume of our diluted solution is 250 milliliters. And our initial concentration was 5.0 molar. Our molar units cancel out. Do our math right here. We find that we will need 5 milliliters of our concentrated solution to make this particular diluted solution. And lastly, if 10 milliliters of a 10 molar stock solution of sodium hydroxide is diluted to 250, what is the concentration of the stock solution? Okay, so again, we're using the formula for dilution, but we're going to be solving this time for MD. Okay, so we're going to have MD equal to MC times VC over VD. And so now we are going to substitute our values in, and we're going to have our initial concentration of 10 molar. We're going to have our initial volume of 10.0 milliliters. And we're going to divide it by our final diluted volume of 250 milliliters. Okay, the milliliters are going to cancel each other out, leaving us with a unit of molarity. And so we're going to do our math skills again. We're going to find out that we're going to have a new concentration of 0.40 molar sodium hydroxide. Again, just like what we saw with the molarity formulas, we could take this formula and rearrange it to solve for any of these 4 substances. Okay. The key thing is reading the question carefully, identifying what values go with what variable. Okay. If it's helpful, over on the side of your page, before you even finalize what is, what your formula is, just put down MC. MD, VC, VD, and just read the question carefully, identifying, then identify what you are trying to solve for, and then place the appropriate values to the appropriate variables. Okay, I do that a lot of times in my math problems, just so I can give an identity to my values and variables. Okay, so anyway, that is section 5. We've only got one more section to go for the semester, okay? And so this is where we are going to use molarities and stoichiometry together. Yay, you're never going to get rid of it. But again, as you see here, we got another flow chart, okay? We're going to be talking about titration, okay? Now, it's not going to be too terribly long of a discussion, but I do want to go over some of the problems here, okay? So with that being said, I'm going to sign off here. If you have any questions on this, just give me a shout. Until then, however, I will see you later. Bye-bye.